everybody, welcome back. I'm Álvaro Coutinho, and I'm glad to have you here today with us for our program that starts today with our industry talk. I would like to call Professor Cray Moita, who will be sharing this session today. Please, Cray.
Hello, Álvaro. Hello, everybody. And good day for everybody. Morning in Brazil, afternoon in Europe, evening in Asia. Hope everybody is fine. And I'm here to present the talk, the industrial talk that's going to be given by Dr. Gunter Roeth, who will be talking to us about accelerating HPC+AI science workflow using physics-informed neural network. It's a pleasure for me to be here and to introduce this talk. Dr. Gunter Roeth joined NVIDIA in Paris as a solution architect in October 2014, having previously worked at Cray, HP, Sun Microsystems, and most recently at Bull. He has a master in geophysics from the Institut of the Physique du Globe, IPG, in Paris, and has completed a PhD in seismology, it's a difficult name to say, on the use of neural network, artificial intelligence for interpreting geophysical data. Well, we would like to welcome Dr. Gunter Roeth. And Dr. Gunther, are you there? You can join us now.
Yes.
Okay, there you are.
Thank you very much.
And again, a very warm welcome to you.
Okay.
And you feel free. You have the screen, not the floor. You have the screen now to talk to us. And we're going to be enjoying your talk. Thank you very much for your presence.
I think I will cut my camera. Okay, thank you very much. So first of all, I must check a little bit if you can hear me.
Yes, it's fine.
Yes, loud and clear.
Very unstable thing. Okay, very good. So you can hear me and everything. Wonderful. This is very good. Okay, so yes, so welcome everybody to my talk here about accelerating the HPC and AI science workflow using physics-informed neural networks. And my name is Gunter Roeth, and thanks, Mr. Chairman, for this very nice introduction. And it is a big pleasure here to present at your conference, of course. And so without further ado, let me just go into the next slide here in my presentation. And here we see a little bit the challenges that the data center is undergoing these days. And so we see that the traditional HPC that have been very busy, that have kept very busy the data center occupation. So the big simulation is today challenged with a lot of jobs and a lot of interest from researchers to run artificial intelligence, run data analytics. And also what we see more and more is the importance of the visualization. And here in the importance of the visualization, we have to really nicely visualize the results at the end in order to see what we are doing. And then, of course, we have connections to the cloud, and we have also connections here to the edge. And from the edge are actually coming millions of data, millions of tons of new data streaming in every day. And I only pick here 3 examples out of plenty, out of many examples that could be chosen. So every detector upgrade will generate more data, will sample finer, and at the end, bigger files and more files. And here, so we have the square kilometer array. This is in the southern hemisphere. This is where we will simulate the 1 kilometer of a telescope, and then of course we will assemble all these distributed dishes into a central final location. And here with these SKA, we will get approximately 1 exabyte a day. And of course, we have the usual suspects like here for CERN and the fusion energy. And here, what we will do, we are expecting 50 terabytes per day for fusion and 10 times more increase for example, for all the CERN detectors. And so due to the more luminosity. And so who was really happy to have more and more data? Well, neural networks can actually show that the more data you use to train the networks, the better the results will be. And so here, the idea is then, of course, to get a little bit of help here from the neural network, so from the AI community, to do also some processing in the HPC, and then combine it. And here we see the traditional approach on how we would train the network. So we will start here with, we can start from any simulation data here, for example, some astronomic data. We could then just put them together in a training set and train the network to reproduce whatever we want the network to reproduce. And then, of course, the training is still very costful. So this is a very costful process. However, when we come to the inference, so to the deployment, then this is not very time consuming at all, because we only run just like you see on the slide through these couple of layers through the networks. And so inference is generally very quick. And so if we can train now the networks, that may take weeks, yes, of course, but then for the inference, we must, we can run this within a couple of minutes and then have really time-changing results. And here are a couple of areas or domains where we already have successfully implemented this. So the idea here is not to throw away everything that has been written in these 40 years of HPC algorithms, and but now to intelligently combine it with AI. And in this case here, we will combine it now with AI, or a couple of sector segments that have already implemented this. And I mentioned the fusion energy. I mentioned CERN. So in these two domains, they already do this and are following this route. And then, of course, we have all the astrophysics communities, and of course the climate analysis, climate and weather people that are doing this. And here, this is nearly, we find very good use cases. And then, of course, we also have here this all what is medical and or chemical research. And now let us look here a little bit for example, when we speak of this chemical research, now let us speak a little bit. Now let me tell a little bit who have been the 7 out of these 10 of Gordon Bell Prize finalists. And so they are using NVIDIA, and they all combine AI and HPC. And here, of course, we have here on the left, we have this AI-driven multi-scale simulation. And this is the largest massive 305 million atom simulation that is really performed here on the COVID spike protein. And this is done also in combination with NumD. Perhaps you ever heard of NumD. And so this is here for the AI-driven multiscale. And then, of course, we have here the docking analysis. And in docking analysis, we are using Autodock and Rapids and Blazing SQL. And again, this is here 2 billion molecules where we try to find the docking position. And then, of course, we have DeepMDKit, and in DeepMDKit, this have been actually the winner of the last year, Gordon Bell, and they're really pushing the limits of the molecular dynamic with this ab initio accuracy. So this is really a top accuracy. They have found a new way on how to present the molecular atoms, if you like, the molecular orbitals, and so they can be trained or integrated with neural networks. So with the help of neural networks, training small neural networks, you can then train the networks to do these ab initio, wonderful, very good, high precision studies, and they are possible. And then, of course, you can do this one here now on 100 million atoms. So this was have never done before. And then, of course, I already mentioned the square kilometer array. And this square kilometer array is then implemented as a digital twin on Summit with 27,000 GPUs. So these are a couple of last year candidates. And so, of course, this is not all. So we can now look a little bit here on how we can actually implement this one here into this intelligent HPC, because we all know that we have the pre-processing, we have the simulation, and then we have a post-processing step. And so in the pre-processing, for example, we always have some control parameters, some epsilon, some deltas, some, I don't know, some opacity, some cloud formation, and so on, that we just preset as parameters. And so the idea is to do all these kind of things with deep learning. So we can get much better results, of course, with deep learning. The same for simulation. And simulation, we can now help parts of the simulation to be run with deep learning, or just parts of the program, or perhaps the entire simulation. All this is possible. However, what you will see is if we train it only on the data-driven approach, what I've explained until now, then the network has never learned any physical constraints, so may give really stupid answers. And so the idea here is then also to have more information going on, or more constraints from the physical side. And this is possible now by using these physics-informed neural networks. And so we can do this. And then, of course, in the post-processing, visualization is key. And so we can really go through the visualization part here. And And so now this is an important message because normally my slide here would have been SimNet, because SimNet is the product that is doing the physics-informed neural networks. But since Jensen's keynote, so since Tuesday, November 9, so only 2 days ago, Jensen renamed it now from SimNet to Modulus. And so maybe during my presentation, beware with me. So sometimes I say Modulus, sometimes I may say SimNet. And so it is, but when Jensen decides something, you better follow. And here is SIMNet is now called modulus. And so what are the classical domains where we can apply modulus? And here we can, of course, see that modulus can then be applied in all what is this real-time systems. There have never been really a solver, neither some HPC interest or big simulations done for these real-time systems, so digital twins, these autonomous driving, autonomous, all these robot things, and so on and so on. So this sector definitely needs help from AI and can be combined rather easily. And then, of course, we have also one sector just above that is the inverse problems. And inverse problems is a very interesting sector because inverse problems is, for example, in oil and gas or medical imaging or climate or whatever you name it. So these are very, very heavy problems. So they may stay in the computer for weeks or for days and weeks. And then you compute one solution, but you don't want one solution. What you want, because you know that oil is not at one particular location. You can only compute one particular solution, but you know that reality has more or less a distribution of then the oil and so on. So you really would like to to simulate this. So here in all these simulations, we would like to really speed them up. And then at the end, get some statistical, sampling, or see a video or film, an animation of the Earth, or of the climate changes, and so on and so on. And then let us decide which are the reasonable things and what can be extracted. And then, of course, we have the digital design and manufacturing, and this one is also a very important factor here. And here we will do the digital design exploration. And I will have a couple of examples here on this one. And as already said, we have the CFD, we have molecular dynamics and so on, radiation. And we have already a couple of use cases here for modulus that are correctly applied. And now let us look a little bit, what is modulus? And modulus is really an advanced networks. And it is an entire stack, so you can basically download it, run it in a container. And it is really an architecture that is allows you also to rewrite things. It is written in SymPy, Python dialect, and using TensorFlow, and so you can really take it from there and go on. And it is I will show a lot of cases where we can see that the parameterization is really easy to do. And so it is easy to train for the parameterized geometries. And then you can just run over the design space and have a first exploration, at least, of this design space. And as already said, it runs out of the box. It runs in a container. It runs multi-GPU. It runs multi-node. And it can be compiled with the TensorFlow XLA compiler. You can use automatic mix precision and so on. So all these features are automatically enabled in. And then, of course, we have a really wonderful user's guide. And because each chapter, if you like, of the user's guide is like a little bit like a small guided example. And so you start perhaps with the easiest ones, and then you go through more and more difficult examples and so on until you come to the end. So the user's guide here is fantastic and very good, very well written tool. And then, of course, we hope that the API gets standardized and utilized by a lot of people. And so as already said, so here on the left we see the supervised approach, and on the left we see this traditional learning, so traditional learning, and here we would he would train here for simulation data, the network, the multi-layered network or convolutional network, it doesn't matter. And then the network would find a set of weights that minimizes the error between the compute and the desired output. And then the training is done and we can go in inference. However, as already said, this network does not have any idea about physics. So I have no ideas about temperature. I don't know, perhaps your particular experiments are limited between 0 and 100 degrees, so it has no idea about this. For example, when you predict the Earth or lake temperature examples or so, and then you know when you go deeper in the Earth or in the lake, the temperature increases, so you have a positive temperature gradient and all this kind of thing. The network knows nothing. And so how can we now make it aware? And of course, we can just simply put the more and more constraints in the loss function. So this is, of course, one possibility. Or what we can also do, because we know that the neural networks are universal approximators, and just use the neural networks, but this time make them really dependent on time and space, and that let us also to have the possibility to compute the derivative. And in this case, we would now set up a network that depends here on, for example, here in this case, that depends on X and Y, so the spatial coordinates that implements the partial differential equation, because I can then compute these partial derivatives with respect to X and Y throughout at the end of the network and backpropagate them. And then the idea here is now to, as already said, so we will now put the constraints now really here in the loss. So the loss is really where we play with the training of the network. So now let us look a little bit here. So for example, we have here on the top, we have this differential operator. So the first derivative with respect to t, and then we have the differential operator, and then this equation is equal to 0. And this one here, so as already said, so this one here depends, of course, on x and t. So our network will have as x input the spatial coordinates x and the time coordinate t. And then the output, which should be, of course, the whatever this partial differential equation is implementing. This may be, for example, a wave equation or wave propagation or CFD or whatever. And so the output would then be, for example, a wave field or the fluid flow of this x and t input as an output then, okay? And so we would have to set it up like this. The network is just as normal. However, here then the network will have to find a solution. And how can we do this? Well, when you look at the right, at the formulation of the differential operator, we say that this one is equal to 0. What else, or when else have you seen this constraint that something should be equal to 0? Well, when you train neural networks, you ask to find to minimize the error, so equal to 0, when between the compute and the desired output. So this is nothing else. So we can directly use the differential operator and put it here in the loss function. And this is how we how these physics-informed networks are defined or used. So the differential operator is used in the loss function, and directly, because it has to be equal to 0. So we can directly, instead of putting it to 0, we can say, okay, we minimize it by the network, and then directly have the differential operator or differential equation in the loss function. In the same way, because where the differential equation is mostly not has still too many solutions. So we need the initial conditions, we need boundary conditions, and in the same way as we define the differential operator, we can also define the same losses here now for the initial conditions and the boundary conditions, and then compute the entire loss with the residual loss from the and plus the boundary losses, or the boundary loss and the initial condition loss. And this is graphically how we are doing it. And so we have the boundary condition, we have the initial condition loss, and then we have the residual loss from the differential operator, and then they are combined, and they're not. It is not a linear combination. CILAMCE is much more clever here because it will automatically do a lot of loss weighting. One of the biggest added values of CILAMCE is its loss weighting. And then, like in normal networks, so we just backpropagate the loss now. However, then we also have to compute the partial derivatives with respect to t and x, so this is to whatever it depends. And this, of course, we can do this with automatic differentiation that is automatically in the frameworks. And here we see a little bit how this is then implemented in CILAMCE. So we have an input. So we get here, for example, the time or perhaps not time. And then we have the spatial coordinates. We have an output here, for example, horizontal and velocity and pressure. And so this is from and then in between we have the hidden layers. So this is just fully connected layers. And you have different possibilities then to define how many you use, how many neurons you use per layer, and so on. But this is basically the setup. And then, of course, we have at the end, we have one additional layer to for every derivative of the partial differential equation. So we could go up to nth derivative, but generally the problems that I'm showing, and also seismic and so on, it's only a second order derivative. So we only need these second order derivatives here. And so this is now how it is implemented in CILAMCE. And CILAMCE is already, I don't want to go through the whole list, but because since a couple of years, there have been a lot of publications, and CILAMCE is really implementing. So with a single call, you can then, for example, call the Fourier features. You can have the Gaussian encoding. You can do the sinusoidal representations. You can use the modified Fourier features, and so on and so on. So you will compute better gradients, or you will improve the gradient quality. You will have better convergence, because, and so on and so on. So a lot of things have been published here, and they are already implemented in CILAMCE, and then you could just call them throughout, with the TensorFlow Python syntax. And this is a little bit the idea. And here are, again, I don't go through the whole list there, but just to give you an idea, this is really state-of-the-art implementation. We work every day to improve it. Every day when we find a new publication that comes out, and we try really to keep it up to date. Now let us look a little bit here, for example, at these partial differential equations, and here what we see is an example here from the CFD 2D lit-driven, the 2D lit-driven cavity case, and here we have the continuous equation and the momentum in the equations. And then, of course, we can have, and then we have the, just hold a while. Yeah. And then, of course, we can put these ones here directly into CILAMCE, and then we will have to do some sampling. And the sampling is done here on this domain. And this is, you see here the lit-driven cavity domain. And you can see that you sample, of course, on the boundaries, and you also do some random sampling inside the domain. And then you give this as input, and then and then CILAMCE will, or Modulus will learn modulus will learn how to simulate these, how to simulate these differential equation, these CFD. Yeah. And sorry. And the results are always, of course, very good because when we see that, well, anyway, it is always difficult to compare because here in this world, or in the real world, first of all, there is not a single answer again for any of these experiments. But sometimes we have to go very high or very fine sampling with the solvers and so on, or with standard tools and so on. So here we compare it against OpenFOAM, and we see that this is a very, very good accordance. And now let me, and of course, we can also set up a little bit more complex things. So here, for example, we have a heatsink, and in a heatsink, you will see, so this is how a heatsink looks like. So a heatsink is just a processor, a chip, and then you have this heat evaporators put on it. Okay, so this is a little bit the idea of the heatsink. And here we can now also do this, we can also implement this one here with SimNet or with Modulus. And in this case, we will have to, we are having 3 differential equations and or 3 networks even. So the first one is then, of course, for the CFD that is doing the turbulent CFD. And in this case, we have implemented the Navier-Stokes here. And again, we write directly equals 0. And so we can directly minimize it. And then there is the heat transfer in the fluid, because we have the heat transfer, first of all, in the fluid. And then we have the heat transfer in the solid as well. So these are the 3 networks. We run one, we train one after the other. We run then in inference one after the other. And so this is also the idea here, to have more complex configurations and more complex setups that are possible. And then here, for example, and then here I already mentioned a couple of these design space explorations. And here we see, for example, these are the different choices that we have tested on, that we have implemented with SimNet. And here, for example, we test for the one of the possibilities to vary to have this one is then the inlet velocity. So we have variable inlet velocity. We have different thickness level in the beginning. We have a front length adjustment. We have a top front trim angle, a bottom front trim angle, and so on and so on. So all over the places, we really try to compute then the solution, and then for the best combination out of these 10 different parameters. And this one before, it's just not possible, because you would run forever your simulation. And so here now we can do it, and so now we can really run over the design space, and we can do the design space exploration. And then, of course, when we look a little bit here at the different visualizations, and especially for the heatsink, we want to be in a certain configuration for pressure drop, and at a certain temperature. We will not exceed a certain temperature, or we will be around a certain temperature, and we will avoid these strange pressure drops. And so these are a little bit things to avoid here when we do the heat sinks. And here we see that the solution from SimNet is pretty much in correspondence with the commercial solver, with OpenFOAM, and so we can so we have validated this. But again, it is these are not easy validations. And now let us look a little bit here, for example, at the improved physics and predictions. And here we have, as first example, the example here from Frederick Cedric Fresses from Stanford, and here he's actually implementing the PINS modulus with the Buckley-Leverett equation. The Buckley-Leverett equation is a fluid flow equation, and that is used in the reservoir modeling. So the reservoir modeling is based on this one here. And so we will have, and he will implement this with SimNet after a first trial where he concluded that it would have been difficult, or that the network, physics-informed networks would have been difficult to be used. And however, the first one was used without SimNet, and then the second try he was using SimNet, and it is of course a much better starting point in order to implement everything. And then he could also finally implement everything successfully. And what you see here is that the fluid flow, or the fluid transports then through the medium and is replaced. And it fits very well with the solution, with the theoretical solution. And to compute also the theoretical solution, when you look a little bit at the reservoir, again, there's not a unique solution, and but you will have to apply certain shock waves and certain criteria, shockwave criteria, velocities, and also entropy, in order to get rid of non-physical solutions. And this is all and this is all validated. And this year he will present at GTC. This week he will present some follow-up study of this study. But this one here is really impressive. And then of course we have here the seismic problem now. And so here it's a seismic problem. We just have the normal wave equation and the acoustic wave equation in this case. And in this case, this one here is then defined as a square of the slowness. And then you have the second order derivatives of time plus the spatial derivatives. And generally this is implemented with finite differences or finite elements. And this work here. And then you can see that the waves are propagating very, very nicely throughout the domain. And then, for example, what we also have in SimNet, we have the possibility to have all these boundary conditions that can be implemented today in SimNet. So there's a wide choice of boundary conditions to get all this done here successfully. And also what is nicely is, and this is, I don't know if you can see it. No, there is not such an example anyway, but where SimNet is even better than the prediction, because prediction are things that are reflections back. Oh yes, there are a couple of reflections back. But anyway, so yeah. And here's also another study, and this one here is then, for example, the seismic problem, again, the acoustic wave equation. And we see it here that we have the point cloud representation that we sample into the into the neural network. And then we run through the network. We will compute the wave field as output, and then we will compute the different PDEs. And the PDEs are just the PDEs that I have shown. And we have initial condition, we have the boundary conditions, and then we can just compile the entire loss, and the network will learn it. However, here Harpreet has done, or interim, when he did this, he was actually forced to oblige to multiply the input field with t-square in order to have a hard constraint or hard constraint on this initial condition. So this is what he was using. And but if you do this, then We can now also look at, for example, here, before we have seen just a homogeneous medium, and now we can look at the 3-layer velocity. And we can see that the waves propagate also very nicely here. So we have these 3 layers with a source in the middle. And now we can see that the waves are propagating around the source. And here they are diffracted a little bit on the different layers. And again, and then we come to the end. And then we look, for example, at this certain position here. And then we can have a look at it, and then we can see that the solution is really close to what is the actual solution. And again, I really highly recommend to watch Harpreet City, who has done all this work and who has presented this at the GTC this year. So 2 days. Oh, it's ending today. GTC is ending today. So just try to catch up with him and catch up with his presentation. And and then I just wanted to show a couple of more use cases here. And this one is from Philippe Viana, and this one here is really to compute a digital twin, where we want to compute really the we want to compute the stress accumulation when airplanes travel. So here, for example, we see that we have an aircraft fuselage and with windows, and we know every time the aircraft travels or goes in the air, then we will have some cracks or something accumulating on the windows, and this is what we were simulating here. And so the idea here is then to have these crack growth. This is in the far left corner. This is the most important thing. So the crack growth K, delta K, and normally is very difficult to express. So sometimes you just say it is assumed. However, it should be really a function of the height and distance that the airplane has traveled. Okay. And then the crack growth is, of course, can be described as an accumulation of these stress intensities, and by the Paris law. And this is then implemented in a recurrent neural network. So here you see in the middle, you see that this is a recurrent neural network, a cell of the recurrent neural network, and in every cell we have here a normal ordinary neural network, and then we have the SimNet model, and they both together compute the stress intensity and the Paris law, and this is in every cell of the recurrent neural network. I found this is really impressive. And here are the results, and you see that again with the compared with Abacus, and again the results from SimNet are very good. And then I come here now to one of my favorite showcases, and this one here is this is the parameterized of the Coanda effect. So the Coanda effect is simply a effect where air will attach to solids. Okay, so this is what brings airplanes in the sky and so on. So the Coanda effect is simply this. And here in this this is then done. That's talk from GTC last year. Was done by Kinetic Vision, and these guys have really implemented an air knife, and the air knives are really very universal tools here to blow air. That's all what they do. They blow air. They can blow air to plates. They can blow air to bring temperature down. They can blow air to to bend, and so on and so on. And this particular process, this is the galvanization process where the air knives are used really to cool down the galvanization and to fix it after in the first steps when it comes out of the in this process. And you can see here how these air knives are really built in the sketch here in the middle, in the bottom. And you can see that on the top, it has a very sharp angle and a very, very sharp geometry. However, on the bottom, it has a more circular geometry. And when you play with this circular geometry, then you will see that your flow is actually bending, okay? And when you now blow air through this knife, then you can see that the flow is actually bending. And this is what the small video is showing as well. So here we will see the parameterization of the different, what it has learned. And we can see that the airflow is bending the more, the bigger the circle radius is. So you can basically see this. So now the circle radius is going up again. So now it is going up, and the flow is bending. And then, of course, all this is connected to, in this case, to SolidWorks. So it is directly fed back into SolidWorks, and so we can direct here. So we can really speak of intelligent cut and come in this case here. And so this one here is one of my favorite implementations of SimNet. And then, of course, performance-wise, is I already mentioned, it gets perfectly out of the box, and you should expect linear speed up, or not linear speed up, but very good, nearly linear speed up when you run on problems, when you run on multi-GPU cluster or even a multi-node network. And up and down. And now I come to my conclusion. And so as already said, so you can just download modules from the developer side. You can just download it now. If you have any problems in getting started with, if you have any ideas, just get in touch with me, Gunter R. or Sanjay. And we will be ready to follow this one up here with you. And as already said, there is GTC, and then there is this Colorado School of Mines. This is from Harpreet, the pins for wave propagation. And then we have another one towards developing a high Reynolds number. And then the follow-up here from Frekas to this time he's doing the uncertainty quantification in porous media. And finally, we have the accelerate HPC simulations. And this is a little bit what is now in GTC. And also very important is that we have a GPU container cloud, NGC, where you can download all the containers. And and GTC. And now I come to the end of my talk. Yeah, thanks. That was the end of my talk.
Oh, thank you, Gunther. Very nice talk. Excellent.
Thank you.
Excellent. I think very interesting. And I'll go straight to some of the questions that are here. Because Alvaro has joined us here, I am not going to start with his questions, but I will have a question from Romulo Montavon Silva, and I'm gonna read it. And it says, "Hey Gunter, excellent talk. Are there any plans to include any implementation of just the second order optimizer into SimNet?"
Yes, but it is already in there now. I think our second order optimizer. I don't know what does it mean really.
Well, maybe he can elaborate his questions a little bit later. But if you're saying that it's there already.
It depends what he means with second order operator. So I don't know really what.
All right. Okay. If you can always send another question here. I'm going straight to the questions by Alvaro. Do you want to ask them directly, Alvaro, or can I read it? I read it here. Okay. All right. Gunther, could you please comment on mass conservation of PNN solution?
So we have a special mass conservation mechanism inside the modulus. So you can define actually the mass conservation with these continuity planes. So you can define additional helper planes when you compute these solution, and then you can really have a special implementation of this mass continuity inside modulus. So this is all possible, and doable.
All right. Okay. Thank you. I'm just coming back to the previous question because he actually elaborated a little bit more, and he said that it's something like LBFGS, ADA haste, so on.
LBGF. No, this is not yet working. No, unfortunately not. Yes, so these. Because I'm directly was working with somebody who tried to implement it, and it is and it's not yet easy to implement. It could be because it is an open. You could write it and so on, but for the time being, it is not yet instant. No.
All right. Okay, carry on. I think I interrupted you. I'm sorry.
No, it's okay.
All right, okay. And there is another question by Alvaro here. What about the NN hyperparameters? Is it difficult to choose them?
No, not more difficult than in other neural networks. No, it is really very possible way to do the hyperparameter studies and so on in a controlled way. Yes, this is possible.
Okay, I have a question myself. It's easy to it's a simple question, but I was very curious about it. How easy you mentioned about the manuals and everything, but how easy is actually to set up and to implement to run? Is it something that is straightforward?
It is really straight. Yeah, it is really straight. It is really straightforward. It just runs out of the box. So you download the container. So the easiest, of course, is to download the container, and or you can also do a hardware install. But the container is the easiest. So you download the container, you build the container, and then you go in the container, and then SIMnet comes with a lot of examples. So all these lit driven cavities, the heat sink, the seismic, the CFD, whatever, the stress, and so on and so on. So it comes with a lot of examples already set. And then the user's guide gives you a very nice and very good introduction into any of the cases, and explains you really how to run it. And so you have the data, you have SIMnet running, and you have the user's guide to give you all the explanations. And so it is really a very straightforward way on how to do it. Yeah.
Excellent. Well, I'm looking for, but I can't see any more questions. If there is no more questions, I would like to thank you very much for your talk, for your time to be here, take part in our conference, and the organizers and I thank you very much for this. And I will hand back the chair or the screen to Alvaro, and I hope to see you soon in Brazil in person, not through this remote connection, which is not very good.
Exactly. Yeah, I'm hoping for the same. Yeah.
Okay. Thank you very much, Gunther. Thank you.
It was a real pleasure for me. Real pleasure. And I'm really glad also that we got it all set up and organized. And yeah, it was a real pleasure also from my side. Thanks again.
Thank you, Gunther. Thank you, Ray. It was a fantastic talk. Well, I suggest you all attendants to drop by NVIDIA booth. They have more information there on modules. I would say SimNet, but now it's modules. Thanks for letting us know. And yeah, our group actually have downloaded and implemented and make it available SimNet or modules at the National Center of Supercomputing at the National Lab for Scientific Computing. It's already there. Okay.
Very good.
At least some of them, not everything, but part of it is already there. Okay. Just contact us or NVIDIA guys that you have in the booth, all the contacts, Gunter contacted other guys from NVIDIA if you're interested. Okay. Well, thanks again. Thanks all for joining us. Gunter, fantastic. Thanks so much, NVIDIA, for to bring you here, and it was really great. And guys, we will be back at 2. We have 2 more plenary today at 2 p.m. Rio de Janeiro time. And thank you. See you at 2 o'clock. Thank you, Gunter. See you. Bye-bye.
Thank you. Bye-bye. Bye.